Hello, we've done quite a lot of circuit analysis now, so it's worth knowing how all of these different components work in the circuit. So I'm going to kick off by looking at how we get the energy into the circuits. And one way here is through cells and batteries, which immediately throws up this terminology point that we got a bit of a clash here with how we use the words in an everyday setting and how we're using them in circuits. I mean, really, when we're talking in our physics questions and textbooks, batteries are like the plural of cells, which might sound a bit weird, but if you've just got one of these cells, just one, as we draw on with the symbol, one of those, that's just a cell. We'd quite often describe that as a battery if that was a double A battery that we were putting into something, but it becomes a battery when you then put a second one or more onto a stack of them connected together. Then it becomes a battery. So we've got a difference between cell singular and then battery plural. Yeah, wouldn't get too hung up on that really. We know what we're talking about. So these are working, whether we're talking about cells, batteries, or whatever. We're working from the transfer of chemical energy into electrical energy. So these are electrochemical cells, where we've got a chemical reaction happening inside the cell, and then that is what is driving our electric current. So that's an energy transfer between a chemical store and an electrical store. Now, there's lots of different types of cell. Most notably, we've got alkaline batteries, which are usually our non-rechargeable ones. We've got nickel cadmium ones, which are falling out of favour, but they used to be the main rechargeable batteries that were used, the nickel cadmium ones. There's a lot of restrictions on their production and use nowadays because of environmental damage. And then there's the lithium ion ones, that's ION rather than iron, the metal, which are becoming more and more popular. So I'm just going to run through those three different types rather than trying to cover every single cell that's ever existed. So let's kick off then with the alkaline batteries. So in an alkaline battery, well, as with any battery or cell, I'm probably going to use these two words interchangeably, so don't start getting pedantic with me on those, because really I want to be talking about how they're operating. But if you've got an alkaline battery, or with any battery, we need these two electrodes. We need the negative electrode, this is our anode, and then we need our positive electrode, which is our cathode. And then we're going to need an electrolyte in between the two of them, electrolyte. Right, so in an alkaline battery, we might be looking then at zinc for our anode. We might have something like manganese dioxide, so an MnO2 for our cathode, and then something like potassium hydroxide, KOH, as our electrolyte. So as we're going to see this also in the nickel cadmium batteries as well, this is a reduction oxidation reaction that we've got happening here. So at the anode, this is so when you look at a battery, if you've got your double A battery and you've got the positive and the negative marked on, so here we've got the negative, we're looking at the anode here. So this is the zinc. So the zinc reacts with so in our electrolyte, this has now split. We've got K plus and we've got OH minus. So that's split in our electrolyte. The zinc is then reacting with the hydroxide bit, the OH minus. And that is then oxidizing the zinc. So this is our, when I was saying reduction oxidation reaction, so we've got oxidation going on there, producing some water and some electrons. So the zinc ion, the positive zinc, our zinc 2 plus, has gone into the electrolyte. So we're actually dissolving the zinc off here. And it's leaving these electrons on the zinc anode. That's why it's becoming negative. These electrons are getting left behind. Whereas on the cathode, we're getting that that cathode is then going to be losing electrons into the electrolyte. So we're going to get a reduction reaction. I'm not going to write all of these things out because I'm not doing well, I suppose I could do. We've got a 2MnO2 plus the 2H2O plus 2 electrons. And then you get this reduction reaction going on. I wouldn't worry about this too much if you're not a chemist. But these electrons are coming off of the cathode, leaving it positive, and these electrons are staying on the anode, making it negative. This is how we're getting our potential difference between the two plates. So it's a way of, they're not the same electrons, but it's a way of passing electrons, in inverted commas, from the cathode to the anode. This is driven by the energy release from breaking these chemical bonds. So if we're getting this build up of charge, then we're having to do work here. We need an energy release in order to get energy into our circuit, and that's coming from the chemical energy store. And this is the process that's happening inside the battery. If you've got one of your AA's or AAA's or whatever, and we're getting this build up of electrons on the zinc anode and a build up of positive charge on the cathode. That's creating that potential difference. That's driving the current. Now, with these batteries, I mean, let's look at the internal structure of them. So you've got the casing of the battery. We've got the plus. Our cathode is the lumpy bit at the top, and the cathode is on the outside of this battery. The negative terminal, the anode, is at the bottom. So this is a conductor at the bottom here, which is connected to a pin that sort of goes inside the battery, which is then surrounded by the anode. So this bit here, this sort of dotted bit around here, that's the anode. This bit here that I'm putting these crosses in, that's the cathode. So they're quite big areas. It's not just like, oh, you've got some kind of flat plate or something like that. It's not just the lumps at the end. Okay, these are the terminals that we're connecting the circuit onto. But the anode and the cathode are quite large on the inside. Now, the internal resistance that you get in these batteries, I mean, a lot of that is coming from the casing, really. So we've got this metal casing, which is part of connecting up to the terminals at either end of the batteries. So if you've got a larger casing, then you're going to have a lower internal resistance. So just having a bigger battery physically, in terms of the size of it, is going to reduce the internal resistance of the battery, which means you're going to be able to get a higher current. And if you've got a AA battery, you can maybe draw about 0.7 amps from a AA before it starts getting noticeably hot. If you want to get a larger current, because that's what is really going to be heating up your cell or your battery, if you want a larger current, well, you need a lower internal resistance in order to keep the temperature down. Think of our I squared R for the power. So if this is our internal resistance, if you want to push your current up, we need to drop that down so that our power dissipated in the cell is coming down. So you're going to want a larger battery. You're going to want like a D cell or something like that. If you've got a D cell, it's just bigger. So we've got lower internal resistance. So that's how your alkaline battery is working. Now, if we move over to then nickel cadmium. Now, these are quite similar. This is another reduction oxidation process. So we've got a similar process, but we've got different anode, cathode. We've got different materials going on here. So our anode, our cathode, our electrolyte. Well, the electrolyte, you quite often have the same thing. I mean, potassium hydroxide is useful stuff when it comes to cells. But then the anode and the cathode, this is where we're getting the nickel and the cadmium. So the cadmium is the anode, the nickel is the cathode, or some nickel compound anyway. It might be, some kind of hydroxide type thing going on. We're going to have some compound of nickel anyway, which is kicking around. And you've got very similar things. I'm not going to write out the chemical equations again, because there's so much variation in what you might have at the anode and the cathode, and also, to be honest, I can't remember what they all are now, so I'd probably end up making a mistake. These were the ones that I had reminded myself of in advance. But you've got a similar thing going on where you're going to be getting a build-up of electrons on the anode, and you're going to have electrons then donated from the nickel. So this is going to end up being positive, that's going to end up being negative. But it's the same chemical principles that are applying. You've got reduction and you've got oxidation. Nickel cadmium batteries, as I mentioned earlier on, there's restrictions on them now because of the environmental impact of disposal. I know in the EU, as far as I'm aware anyway, they're manufactured to replace ones that are already being used, but not for new use. So the production and use of them is limited now. The main advantage that the nickel cadmium cells had, particularly if you're going to start comparing them to lithium ion, which I'm going to get onto in a second, the main advantage is these nickel cadmium cells, they can discharge their full energy capacity very, very quickly without damaging themselves, much quicker than a lithium ion cell can. So they do have that advantage, and that's why it's not easy to just say, we're going to stop using these now, because if you want to have that high energy discharge rate, then they're quite often still the go-to cell to be using. But they're quite similar, and these can be recharged in a way that you can't with these alkaline ones. I mean, we can see here how the zinc is getting used up here. But the nickel cadmium, the processes here are, to a certain extent, up to a limit, they're reversible. So when you plug them in with reverse polarity and then you're passing electricity back in, you can reverse the chemical process to some extent. It works fairly well, but you're getting a loss of efficiency and a loss of reversibility every time it's done. I mean, we see this with rechargeable batteries. They quite often say you can recharge them 1,000 times, which often seemed optimistic from my recollection of using these things in the past. But you still get a pretty good life out of them and a pretty good number of recharges before they just die on you. Now, lithium ion, these work in a different way. So we've now got, and they've also got much more variety in the chemistry that's behind all of this. But these have certain advantages. I've already spoken about one disadvantage compared to the nickel cadmium in terms of the energy discharge rate, if you want that. But these have a longer life than nickel cadmium. They have a longer recycle life, which is why we're using these things in mobile phones and electric cars and such like. You're charging your phone up every day, if not multiple times a day. And okay, the batteries eventually start getting knackered, but that's a lot of recharging that you're getting out of that cell. So they've certainly got an advantage in terms of their recycle life. And they've also got a much higher energy density, so they can be quite small. And you see that in some of the little pill cells, the circular ones that you put in things. I mean, these are really small cells. Lithium is, it's small for a start. I mean, that helps in terms of getting the energy density up. And you start getting into then the intricacies of different bonding between electron shells. So, when you're in your S and your P shells, the inner shells, then you're getting more energy than when you've got D bonding. So when you're in your transition elements, then, as we are with our zinc and with our nickel and our cadmium, you haven't got as higher energy density as you have with something like lithium when you're earlier on in the periodic table. So we're getting that higher energy density. But we've got a new chemical process, which, to be honest, I don't know an enormous amount about. But we got this thing called intercalation, which is the sort of foundational mechanism inside these lithium ion batteries. And this means you can take these positive lithium ions, and you can insert them inside structures. So say we've got our anode here might be carbon, our cathode might be, well, you're going to want some kind of metal oxide. So we've got a metal oxide. I mean, this might be, so we've got lithium, I don't know, it might be with some iron, with some cobalt, with nickel or something else. We've got some kind of combinations of, we've got a metal oxide, like one of these iron, cobalt, nickel. We got that as an oxide. And this lithium, it can insert inside that oxide, or it can insert inside the carbon structure. So it can slip in and out of the anode and the cathode. In the electrolyte, and the electrolyte is different here because we want to have some kind of salt. So by salt, we're talking about ions, an ionic compound, like we've got here. We've got our positive and our negative ions. And we're going to have a lithium salt because we need these Li+, we need our positive lithium ions. But you don't want to be putting lithium into water because things go boom when you start doing that. Lithium reacts with water quite vigorously. It produces hydrogen gas. We don't really want that. So you need a different sort of solvent here. So you're looking at some kind of organic solvent to dissolve your lithium salt. And then these lithium ions can move in either direction depending on whether we're charging or discharging. So we're wanting to, we want our anode to be negative. We want our cathode to be positive when we're then powering our circuit. So we're getting these positive lithium ions, which are moving then one direction to get this split in charge. So we're getting the positive charges moving over to the cathode. And then when we're doing that and we want to recharge, then we're plugging it into our reverse polarity on the electricity source to recharge it, to move all of our lithium ions back again. So we're shoving them back into the carbon. So we've got this intercalation process. And like I say, all I really know about intercalation is this talking about this insertion of ions into larger structures. I don't understand the chemistry any more than that. So that's how these lithium ion cells are working. And this process of dealing with intercalation is much more reversible. And that's what gives the much longer recycle life of those cells. So yeah, different sort of structures here of how we're setting them up, but they're all working off of some basic ideas. We have to have the anode, we have to have the cathode, we have to have the electrolyte. We have to set up a potential difference between the anode and the cathode by getting a build-up of negative charge on the anode and a build-up of positive charge on the cathode. And then when we connect that to our circuit, that potential difference is then what's driving our electric current and powering everything else in the circuit. So there you go. That's an overview of cells and batteries.